I got hit. No. All right. Okay. And I got another delay for some reason. Am I doing something wrong? What do I have going on my computer? Does that make a difference? Let me shut everything off. Let's see. I've got two Zoom windows down here. Maybe that's it. Am I making a... Did I already have a Zoom open when I got started here today? I wasn't logged out of everything. It doesn't seem that way. Well, maybe, hang on one more second here. I'm going to stop sharing. Try this all again. I don't think I want that. I think that'll cancel our meeting. All right, I'm going to try it another time here. See if we can get this to hop up. All right, well, at the moment that looks good. And it's back to the way it was. So hopefully we won't lose anything. All right, well, sorry for that delay. All right, so I'm gonna begin. Let's see, this problem from the practice exam was number 5, practice exam. And it said something along these lines. It has this sheet, is it what it calls a sheet? I was going to say plate, but maybe I should stick to the same words. So I'll just kind of draw, maybe try to do my best for a 3-dimensional, have like a piece of metal, little strap or something that would look like that. But it kind of would look like, grab my sticky here. And so if my drawing's coming across in 3 dimensions, maybe I'll take a little sticky note here. But this is what I'm trying to do, is say, okay, I have kind of a thin piece of sheet here, and it's pointing out, I guess, towards the camera. And if I come out perpendicular, as they say, a distance D over here, what is the magnetic field if this whole sheet is carrying a current of I? And the fundamental idea of this is that we've done wires. So you might think of this, I better not be green, I'll say green for the magnetic field. So maybe in this light blue, I'll say you could think of this as a wire going back, stacked on another wire. And so it kind of looked like this, a wire, a wire, a wire, a wire, each of them going back. And so mathematically, what I'm trying to say here is that then the total field would be the sum of the field from a bunch of wires. And of course, the field from a wire is the mu naught I over 2 pi r. That's the magnitude of it. And so if you'll let me kind of redraw this, I'll put a page 1 up here. But if you let me redraw this as a cross section, then it might look something like this. So I'll have this strip there pointing down. And then perpendicular would be off to the side, some distance d.
I think the camera froze.
Oh, yeah, I just saw that. Okay. Oh, now in that case, I think I know that one. Like I said, it was asleep. I never changed the setting to never go to sleep. Are we back to real? Oh, good. Yeah. All right. Yeah, got to do that before start time. Okay, so I think it froze when I was just starting to draw this sheet here. So this is a cross section of this. Tried to do a three-dimensional one here, and I'm trying to find the magnetic field here. So the key is to maybe pick some random little chunk of it and say, all right, right there, let's look at that little chunk. So that little wire right there going all the way back. What would be the magnetic field from that one? And then I would say that's the magnetic field from one wire. And then I'm going to add up an infinite number of wires to get the total. Okay, so we already have said, and I'll repeat it, this would be the mathematical equation of what is the value of the field. Right? And the direction of the field is where right-hand rule number 2 comes into play, where I would, hold my right hand with a thumbs up approach, and I'm going to point it in the direction of the current, so that's trying to get it towards the camera there, and then that's my thumb is the current, and then my fingers will be the field in this case, and so maybe it's worth repeating. I hope that video I sent out on the right-hand rule helped, but this right-hand rule, you can't say that the current is always your thumb or always your fingers, because you use your thumb or your fingers for the current depending on the shape of your current. So what I have is a straight current, so I'm going to use my thumb for the current, and so my fingers are going to be the field. So if I hold it this way, the field would make these big circles around here. So the field would be pointing off in this direction. Now, the reason it's important that we understand the direction of that field is because we're adding a bunch of vectors together. And so this is better written as vectors. And so you have to put X components with X components and Y components with Y components. And of course, adding vectors is a little bit harder. But luckily for us, if you look at what I keep calling the symmetric twin, since we're getting the field right along the perpendicular bisector of this, then this right here, if I put my right hand, would make a field that arcs around and looks something like this. And so all the fields that are above this midline would kind of arc out in this direction. I guess I would say they would be up and to the right from everything up here, and everything down here would be up and to the left. And so since they have a symmetric twin, all the lefts and rights would cancel off. And so if we call this the traditional x-axis, I suppose the first thing I can do is to say the magnetic field in the x direction is going to come out to be 0. and maybe I should say I am kind of thinking about the traditional XYZ coordinate system. And so I, you might even say I'm halfway done because I've got the field in the X direction already. Now I just need to do the Y direction. I suppose you could even argue the Z direction is also zero. Although I don't think I would say I'm 2/3 done. I still got a lot of work to do here. But the real work then is to find the Y component here. And so coming back to this magnetic field here, which is coming from this current here, I'll make a little dotted line. This is the R, and that doesn't show up real well. Maybe I should stay away from the orange. How about a darker blue? So this dotted line is the distance R that this point where I want to get the field is from this wire that is creating the field. And it's up at this angle. And of course, it depends on what angle you want to define it. In my mind, for some reason, I was thinking of a vertical line and calling this angle theta, so that the field in the Y direction would be the field multiplied by cosine of theta. And so I need to find the magnitude of the field and put that here. And then I also need to multiply it by cosine of theta. So let me go to a second page here. So I would say, all right, page 2, the field in the Y direction is the magnitude of the field times cosine of that angle. Okay. And then the magnitude is this mu naught times the current over the 2 pi r. And we've got a lot more talking about that one. And then cosine of theta, and we got a lot more talking about that one also. Let me start here with the currents and come back to my picture. This little I here, of course, means the current in this wire right here. Don't confuse it with the I that was given in the problem. I given in the problem is the entire current within the sheet. And that's not what I'm talking about here. I'm talking about a little partial piece of the whole current. Okay, so I'm going to come back over here and call this, kind of using my calculus, if you will, a DI, a small amount of current. The whole current is I, but this is better written as in this little piece right here, this is a DI. So how much of the whole current? So like I said, that's just a little piece. And so it's probably best then to continue with the calculus on the other side of the equation and call it a small bit of the vertical component of the magnetic field, because the whole magnetic field is what I'm going to get when I add up all of the vertical components of this piece and this piece and this piece and this piece and this piece. Okay. Now, down here, there is a 2 pi r. Now, again, let's remember what r is. Let's go back to page 1. R is the distance away, or the distance between the point where we want to find the magnetic field and the source of the magnetic field, the current. So that's why I labeled this as an R. It would be here. And so if the horizontal distance is d, and we let this vertical distance be represented by a variable y, see, and that's what's going to change, is we're going to be talking about different vertical positions of y as we add it up, and we get the total magnetic field. We could do a Pythagorean's theorem to get r, because we could take the horizontal distance squared and the vertical distance squared and then take its square root. So I'm going to write this over here on page 2 as a d squared plus a y squared. So that formula right there is the magnitude of it. And then I've got this piece here, which is cosine of the angle. Okay, well, let me come back to my picture. I labeled this as theta, and I want cosine of it. And that's true, but watch this for a moment here. We know that the magnetic field is perpendicular to this line, so coming from the source. So I guess I'd say that's 90 degrees. We also know that this blue vertical line and this distance d is also, let me put it here, 90 degrees. Now, these two 90 degrees each share this much from the vertical here to this blue line. So in other words, this blue line to the vertical plus theta is 90 degrees. But also this blue line to the vertical and this angle here add up to 90 degrees. So that would tell me that this down here is also a theta. And so I started this problem thinking about this angle theta because I wanted the adjacent piece of it. But now I'm going to change my attention over to here where I can say, okay, this is the angle I'm going to focus my attention on, this theta. And cosine of it would be the adjacent, so that's the d over the hypotenuse. All right, so coming back to where we are here on page 2, cosine of theta can be written as a d over the square root of d squared plus y squared. And so that would be simplified a little bit by saying I have a mu naught, I have a d, I have the current, di, I have a 2 pi, and now I have a d squared plus a y squared when I put those two square roots together. So there's the vertical component of the magnetic field. And of course, now I want to add them together, but I do want to make a little, additional step here because this is the current that's in that little rectangular piece. Okay, so coming back over to this picture. And kind of what we did, if you remember doing this, we did a lot of this with, I guess, Coulomb's law and Gauss's law. Now, in those cases, we were looking at electric field, and the source of the electric field was the charges. Here, the source is the current. But I'm going to play the same kind of game. I'll call it a density game. Because I could say if I looked at this object that had a width, and now I guess I need to jump back to the picture here. Oh, good. It's called L in the picture here. Okay. If I took the whole current, which is I, and divided it by its whole width, so that whole current is spread out on a vertical line of L, that should be equal to a little bit of current, so the little bit of current that is in that one little wire, divided by the width of that one little tiny wire. So I'm going to call it a dy. So that means I can write a little bit of current as an I over an L times a dy. Okay. So coming back here to page 2, then I'm going to write this di as I over L dy. That's this di. So I'll just cross out that di and put what's equal to it. Okay, so now I guess I would finish the problem by saying, all right, now let's integrate. That is, add up all these little microscopic vertical pieces of the magnetic field. And so this would be a mu naught, a d, an I, and a dy across the top. And in the bottom, there would be a 2 pi and an L, and a d squared and a y squared. And now I'd start to add them up. And then notice, of course, I made this last step purposely so that I can get something, and adding up over space, adding up over a dy. So I had a di, but that wasn't really helpful to solve the problem. It was good physics, but not good math. So I needed to switch that physics into a math problem here. And so now I can just add up my dy's. And of course, like any calculus problem, the first thing I like to kind of scan for is things that don't change, because constants can be pulled out of the integral. And so across the numerator here, these three can all be pulled out. In the denominator, the 2 pi and the L can be pulled out. And then, of course, we're just left with this integral. And then, of course, we should also set the limits of it. And we've got, two options here. I'm going to go with the option of saying, let's do this. Let's just imagine this little wire is the first one here at y equals to 0. And I'll just keep going until I get to the top, which would be the position of L over 2 for y. Now, technically, I would have to go down the other direction, but as we mentioned earlier, this is a symmetric twin, so we would get exactly the same thing. So I think to solve this problem, I'm going to just go from 0 to L over 2 and then double that. So I'll just do the top half and realize that the bottom half is the same amount. So I'll just kind of put a factor of 2 in there for just that reason. And in fact, then the factors of 2 can drop off. And then sadly, this one is screaming at me U sub. So let me pause and say, definitely on a test, don't go all the way through and try to do a U sub on this. Let me go to the textbook here and go to the end of it, Appendix B, where we do the mathematics. And this isn't the only way. Of course, remember the test is open book. And where is this one? There it is. And so this one is, of course, listed as a dx. So everywhere I see an x, it's going to be a y for me. And then he's got an a. So everywhere I see an a, it should be a d. Okay, so I'll put a d there. And then he's got the inverse tangent of y over d. All right, so that would be the integral, and then I would evaluate it from 0 to L over 2. All right. Now, I suppose maybe I'll just cancel off those d's, so I get a mu naught, I get an I get a pi over L, and then I get the inverse tangent. And so this would be an L over 2d minus the inverse tangent of 0. Oh, now this is going to make me think about my inverse tangents a little bit. let's see, inverse tangent of 0 must be 0, right? Let me draw a graph here. So this would be something looks like that, right? So yeah, so when the tangent is 0, this is the function tan theta theta. When that's 0, the angle is 0. So that one I can ignore. Inverse tangent of L over 2D. Maybe I should draw another picture here. Kind of. Well, I was going to see if this could simplify, but maybe it's worth stopping right there. Maybe there is no more. I'm going to go to the, let's see, where was this? To the solutions on this. Let's see, I think they list the solutions somewhere. So that's practice test 2. Oh, and here's solutions. Dun, dun, dun. Oh, now I would say we are a little different, but I think this is the, he does a pi over, and he actually does the, oh no, he actually does the solution. That kicked me off. I'm gonna turn that back on. But I guess this is a long way of saying, yes, this is the same one. I'm a little bothered about his inverse tangent. He has 2D over L and not, oh. Okay. Okay. I'm not sure how far to take this, Gina. This is, I think, maybe math that's not quite important here, but maybe just as well. Let me do this. I found it in terms of this angle. And your author, let me call that theta, is doing it in terms of this angle, phi. And of course, if you add those two together, 90 degrees is equal to the phi plus the theta 1. And unless you want me to, but I think I want to stay on the physics. If you were to take the tangents of each of these, we've got some limits issue going on here. Because the trig identity for a tangent, ooh, I believe there's a 1 plus or minus tangent. Yeah, this is where I'm going to ask you in a second here, Gina, if I should stop or keep going. But I kind of leaning towards stopping. I could look this up in Appendix B. And then this one too is a plus or a minus. but what we're going to see is we're going to get this inverse tangent here. We're going to get a pi over 2, and the tangent, bottom line is the tangent of what I got, theta, is the 90 degrees, or he writes it as pi over 2 minus this other angle. And so he writes it in terms of this top angle. I did it in terms of the bottom angle. So I should just say that. I think I'm done. I think this is the answer. I think this is, especially if I was taking an exam, I would just stop there and say, okay, I got the answer. And if I wanted to write it in terms of the other angle, of course, during the test, you would have no idea what angle to do. And I think the angle I picked was a little better, to be quite honest. So, yeah.
Okay, great.
Yeah.
Would you be able to show me? I'm sorry.
Yeah.
Would you be able to show me on the drawing where theta and phi are if you draw out the magnetic line?
Yeah. I think you're talking about this original page, right? Where it's not too messy. And what I call theta is right here. Let's see if I can highlight a triangle. Okay. And maybe this wasn't even the best of triangles to draw, because this is kind of the general triangle, what I call theta. But then when I took the limit, I went all the way up to the top here. So really, the triangle I should have drawn would have been this, okay? So when I come back to my solution, and it says the inverse tangent of, and let me group the L over 2 together. So that's the opposite over the adjacent. So L over 2 is opposite and D is the adjacent. So it's right here, it's this angle. Because it would be the opposite, there's the L over 2, over the adjacent, that's the D. And so this right here, the meaning of inverse tangent of L over 2 over D is this angle. And as a passing note, your author has inverse tangents of D over L over 2, although he does write the 2 up here. And see, that would be this angle, what I'm calling phi. Phi would be then the opposite, so that's D over the adjacent, which is this L over 2. So that's when I saw that, that's how I said, okay, so the author of the solution manual is, or it's not the manual, the solution test, and I think it's Don, if you ever got a chance to meet Don, not to be confused with Ron, but Don then did this angle here, and so that's how I knew he was doing this angle, because I saw this D, and then I saw this L over 2, although he had the 2 simplified up there. So those are the 2 angles I'm talking about in a triangle. The theta is this one, which the adjacent is D, and the opposite is L over 2, and the other angle phi is this one, because the adjacent is the L over 2 and the opposite is the D.
Okay. Would you also be able to tell me or talk more on the density substitution you made? I see why in your picture it'd be obvious why you'd choose dy, but can you talk about that conceptually?
Sure. The
di over dy.
Yeah, okay, so I guess what as I'm solving the problem, and I see this di, the first thought in my head to actually solve it is I can't actually do anything with a di. I need to go back and make it a dy. Now I know a dy because this is what I'm thinking in my mind. I'm thinking in my mind, I'm adding a stack of currents, and the currents are in the y direction. And so what's going on in my head is, how can I take what's in this equation di and switch it to a dy? What is in this problem any kind of connection? And these two variables are a clue to me about density, the density of the current. See if I were to put one on top of the other, and in my mind I might try all kinds of things. That's okay. What if I multiply them together? Well, I multiplying together doesn't really give me anything. Adding them doesn't really give me anything. But you know what does fit this problem really well is that the current is spread out uniformly. It has a density. The current is spread out equally in terms of the vertical axis. So I'm thinking in my mind right here, after, trying to make a connection between these two, realizing that this right here, this dy over dy, is something that I can physically understand in this problem, and it's something that's the same everywhere along here. The current is spread out. So this would say a little bit of current and a little bit of vertical length. And you kind of, I think I've said it a few times on the video. I know I sent you an email on it, that like a chocolate bar, if you take a little tiny square of chocolate and divide it by the area of that chocolate, that gives you the density of that chocolate bar. It's the same as the whole chocolate bar over the whole size of the chocolate bar. So the big over the big is the same as the little over the little. It would be like saying 100, big number, divided by 50, another big number, is actually the same as a small number like 2 divided by 1. So these are the same densities.
Okay, that makes sense. Would the solution change if it wasn't infinite in the z direction?
Definitely, because this equation right here was the equation that was only valid for an infinitely long, and sometimes we just say long wire, because the B sub arts was actually this equation if I do the sine form. And so we can do the sine or the cosine form. But this is actually the equation from a wire. And if the wire goes really, really long, we can replace this angle with 90 degrees and this one with negative 90 degrees. And if it's technically, it has to be infinite long to be 90 degrees. But in practice, if it's super long, if this angle is, 88 degrees, that's close enough. And then we tend to say this would be the formula. So using this formula at the very beginning, right? That was my first step right here on page 2. My very first step was to say the strength of the magnetic field is given by that formula. I have implied in that right away at the beginning that the z direction is really, really long, infinitely long.
Okay, so a variation on this type of problem might be like it's finite and you have to find the angles.
Good point. Yeah. And it wouldn't change by much. You would just have to then have some geometry to figure out that angle. Let's say, it was short enough that the angle, instead of being 90 and 90, and we'll still say it's in the middle, so it comes out to be 60 and negative 60, you would have just started with all those. But all those are constant for every wire. So they would just be a different factor out in front at the end. So yeah, good point. It would be a small variation, and then you would have this factor out in front that would be a result of instead of having a 2 here, we would have a 4, and that 4 would be over whatever, sine of, actually that's pretty easy. Sine of 60 minus, that would be just square root of 3. So this right here would be square root of 3. And I would have a square root of 3 over 4 out in front instead of this 2 out in front.
That 60-degree figure,
Yeah.
not to spend too much time on this, but where did that come from?
Oh, I just made it up saying, what if I had a finite wire?
Oh, gotcha. Okay. We would have to do that using
Right. So
trig.
in the problem, there would have to be, something like in the picture that showed, all right, this is 60 degrees going to the beginning of the current to that point. Yeah.
Okay.
Yeah.
That makes sense. Thank you.
Yeah, you're welcome. Good tough first problem. Woke me up this morning. All right. Okay, so with that in mind, let's see, who was next? I think Andrew. Could you do problem number 3, part 1 on rough practices? Okay, yes, I can here. And yeah, I totally forgot about the practice exam stuff. Okay, but let me put here page 1. Let me go practice tests. And just put practice exam number 3, time is 10:48. And all right, let's do number 3 on the practice exam. Let me switch back then to the practice exam. Oh yeah, I was looking at the solutions. And number 3 says this: a super long straight wire. Now let me just pause there. So we're talking about, super long straight wire. So this is perhaps that equation that I was just working with that only worked for a long straight wire. But keep reading. It looks like the photocopy is not that great, but it says has a radius of capital R and is made of a superconducting material. Superconductors, do not have a uniform current density. But the current density is designed by Mother Nature to have a uniform magnetic field inside the wire. If the current density is radially symmetric, and so they kind of give you the equation here, current density equals some constant B times R to the N, where N is some power and B is some constant. What is the value of N? Oh, excellent question. It's mostly physics, but it looks like there's going to be a little math here because we're trying to find a constant one. But this one, when I see it, is just screaming at me Ampere's law. So let me approach this problem with Ampere's law first. Because we did problems, now not superconductor problems in class, but we did a problem in class where the current density was uniformly distributed inside. It was also done in the textbook. So let me not repeat it unless you really want me to, but I don't think that's the main part of your question. All right, so let me go ahead and on my piece of paper try to draw anyways, a 3-dimensional wire. And here's where I need to draw with my blue one, an Ampean loop. And since we're talking about inside the wire, let me draw an Ampean loop that has a radius of lowercase r. So like all of the Ampere's law going back to Gauss's law, I think one of the tricky parts of it is keeping straight the different r's, the radius of the real physical object and the radius of this ambient loop, because we have to do an integral along this ambient loop, and we have to get the current that goes inside of this ambient loop. But the ambient loop is just a mathematical circle, a mathematical line. And in Gauss's law, it was a mathematical surface. Okay, so coming down to here, this is where the argument of symmetry comes into play, because when you first take that dot product, and so let me just focus on the left-hand side, we need to be able to justify that the magnetic field is some constant value along that ambient loop. So we can pull it out of the integral and therefore do the rest of the problem and then eventually solve for what is the equation of the magnetic field. So I always find it interesting, and I'll keep saying it, that we don't even know what the equation is, yet we are going to justify that it is a constant, at least a constant on the ambient loop. Now in this problem, they are saying that it is a constant, it's uniform everywhere inside of the wire. So that alone tells us it's uniform. But here's our justification on these problems, is we say if you are standing somewhere on here and you look at the current, and in this case, the current may not be uniform. They give us this equation that changes as you go radially outward. And we don't know the power of n. So if n is a positive number, the current gets bigger and bigger as you move out. And if it is a negative number, then it gets smaller and smaller as you move out. But we do know this, that if you were to go on this part of the ambient loop, you move out the same way. So whether it's increasing or decreasing, we don't really know. But if I just kind of make 4 little dots on my ambient loop, I know they come out to be the same value. And so somebody standing on this part of the ambient loop would see the same thing in front of them as behind them, as somebody over here standing looking towards the center. They would see the same thing in front of them and behind them. So the argument goes that the magnitude of the magnetic field must be the same everywhere along the ambient loop, because the magnetic field is created by that current. So there's the justification. Now, the other justification is what I've called lines of anti-symmetry. And maybe orange is a little too close in color. But we argued, and when we did Ampere's law for a wire, so maybe I better not spend too much time on this. Yeah, because I'm just getting into the stuff I think you already know about a straight wire. This is one unique more step. But we argued then that the magnetic field would have to be perpendicular to a line of symmetry, because the current would flip directions and anti-symmetry. So we argued that that would have to be a 0 degrees. And so this side of the equation then would just become the magnetic field, and then of the integral around the ambient loop would be 2 pi, and then I should kind of pause. Would it be 2 pi little r or 2 pi big R? And since we're adding along the ambient loop and the radius of the ambient loop is little r, that would be b times 2 pi little r. So this setup and argument, which I probably spent too much time on, is exactly the same as a wire we did, regardless of it being a superconductor. The one thing that is different is the other side of the equation. So let's talk about the right-hand side of the equation. Because this part here, the current, this is the current that goes inside of the ambient loop. And so if this superconductor has a current of, and they don't really show anything in the picture, and I suppose it's not even relevant for the question, which I guess is why it's not shown. But let me just say that the total current in the superconductor is I, okay? This current that goes through the ambient loop does not equal I. It is not the total current. This would have been a much easier problem if we were asked to find the magnetic field outside the superconductor, because then I would have made an ambient loop outside of the wire, and the current that goes through the ambient loop is all of it, and so the currents would just be I. So what am I going to do? Well, what I'm going to do, and I'll draw a picture, but I'm going to write it mathematically as this symbol. I would say I'm going to add up, well, maybe I better write it first like this. I'm going to add up a bunch of little currents. And so I'm going to draw another picture here, maybe a cross section. So here is the cross section of that wire. And because they told me the current is not uniform, to get the total current in my ambient loop, and so in my cross section, let me draw this ambient loop. And let me draw maybe a ring. And to make it stand out, let me give the ring a little bit of thickness. Maybe I'll color it in here. But I know that the current spread out in this ring is all the same, because they say that the current changes as you go radially outward. And so the next ring out, if I drew another ring here, I don't know that the ring out here has the same current. Again, it may increase or decrease. I don't really know, because I don't know the value of n. And that's, of course, the problem. Find the value of n. But I know that in all these rings that I could add up, because it depends up only on R, they all have the same current density in that ring. And that's going to be the key to this problem, is then I'm going to say that this, and I'll just put the word ring right here, this is the current in a ring. And if I add up all my rings that are inside of my ambient loop, I will get the total current that is inside of my ambient loop. That's really, now that I think about it, the crutch of your question. Because the other side of the equation is just like the wire that we did. All right, so this is the tricky part of the problem. And I'm going to then say that I've got to add up a bunch of rings. So what would be the current in a ring? And now we're going to go back to density like we just did in that last problem. You could do something like this. This thing called J is the current density. And the current density is the current, and I'll just spell it out, current in a given area. So if I'm focusing on this ring, if I want this current here to be the current in one of these rings, then I would want this down here to be the area of a ring, and then this to be the current density of that ring, which is pretty easy to get because that was given to us. So I'm going to replace this right here, the current in a ring, with the J and then the area of the ring. And the current density is given by this constant B, R, to some power of n that we are hunting for. And the area of a ring, so come back over here to this blue ring. It might be a little bit easier to see if you could imagine cutting the ring and laying it straight. Because the area of a ring would be its length and its width. Now, its length would be the circumference, so that would be 2 pi. And I hesitate on calling it an R because I've already used a capital R and a lowercase r. So I'm out of R's. Kind of the normal thing to do is to call it an R prime. And I don't know if that's better or not, because if I call it an R prime, you might think I'm taking the derivative of something. And I don't want you to think that. I just want you to realize that I am talking about the radius of this ring. And of course, that's going to be a variable because each ring, when I add up, gets bigger and bigger. And eventually, the biggest ring I add up is this lowercase r. I never even care about the uppercase. So I hope that isn't confusing by using this r prime. And then the thickness of it would be dr prime too. If I'm going to go ahead and call that an r prime, I might as well say I'm adding up my r prime. Okay, so over here then, I would say the area is 2 pi r prime dr prime, if you want to just list it. Oh, and then I guess I should have called this an r prime too, because this is the density of that ring. It is not the density of the ambient loop, which is at an r. So yeah, that should
Camera
be
froze.
No!
Sorry.
Why do you keep doing that? What's going on here today? All right. Let's see what might be better. Try to reconnect. All right, well, we're back again. All right, so with all that said, we're finally getting to the main part of this problem and this integral, which, as I commented on many problems, including the last one, I like to look for things that are constants. And so they said b was a constant, the 2 pi was a constant. And now I have this integral of r, and it looks like it's an n plus 1. The original factor of n of them is from the given in the problem from the current density. And then the second one is this, what came from the area. And then it's a dr prime. And of course, if we put limits on here, we're adding up from 0 up to, let me switch this back so I can see the camera. Okay, good. And so I'm going from 0 to lowercase r. And so like I said, I think the crutch of your question, now that I see it and I get here, really wasn't this side of the equation. It's this side of the equation where I've got to add up a bunch of rings. Or the hard part is to change the current into current density and then add up a bunch of rings. And the reason I'm going only to lowercase r is because it says that it's only the current inside of the ambient loop. And so I'll be starting with a small ring of radius 0. So r prime is 0. And I'm going to keep adding up these rings until I get to r prime. Now, finally, I can finish this problem, but there is probably a little bit of mathematical stuff here, because when you integrate a power function, you get this r what am I trying to say? You add 1 to the exponent. That's what I'm trying to say. And so this would, I'll just leave it as r prime. And so you would get n plus 1.
The camera froze again.
No! It's crazy. All right. We'll keep trying. We'll keep plugging away here. All right. All right. Okay. Racking my brain, see if I'm doing something different. So it's, crazy. All right. Well, I'll keep going. All right. So I'm not completely sure where it froze, but I was trying to do this integral. And so you have n plus 1, and so you add 1 and then divide by the power. Okay, so there's the integral evaluated from 0 to r. Maybe I should do one more step here in the math, maybe 2. But if I put in the limits, then this r prime actually becomes an r. And I'll put it as n plus 2 and still divided by n plus 2. Now remember, on this side of the equation, I haven't been writing it down, but this is a b times a 2 pi r. And here's the important last step. Maybe I can just squeeze it here on the side. But if I cancel off a 2 pi, and then one of these r's, so this r reduces this to an n plus 1. I get this final equation, mu naught times b times an r, an n plus 1 divided by an n plus 2. And here's the math part of this. This problem said when, and I better just go to another page, when would it equal a constant? And so I have b equals, and there's a bunch of numbers, and then, so I'll go bunch of numbers, r to the n plus 1. So can this ever be a constant? Is there any value of n that would make b then a constant? And absolutely. For example, if, say, you plotted b versus r when n was equal to 0, then you would have r to the 1 power. You would have a line. Well, that's not a constant, obviously. All right. Maybe in a different color, what would I get if n was equal to 1? Well, 1 plus 1 is 2. That would make it quadratic. So it would go like that. Okay. Clearly not a constant. A constant is when you take the variable. So if you plotted y versus x to some power, when that power is 0, that's what a constant is. And so you need to kind of recognize that in the math. So we want n plus 1 to be 0. Because if that is equal to 0, you get this b equals to that stuff in front. You get r to the 0 power, which is just 1. That's how you get it a constant. So that would tell me n has to equal -1. So there's a little bit of science lesson in here. Mother Nature does this on its own, and it distributes the currents in a pattern that apparently looks like this. The current density in a superconductor of this type would be B and it would be r to the -1 power. You might be better off to write it as a b over r. But in terms of doing the test problem, we've discovered what that value of n has to be. So if the current density is distributed as a 1 over r value, you would get a constant magnetic field inside of this conductor. And, turns out nature does that for some very interesting reasons, which I'll pass on, but that's the distribution of the current. That's the way the current has to be distributed in order to have a constant magnetic field inside. So part of this just might be, math, this last step. But the real part of it, hopefully, is this is just applying Ampere's law to figure out what the value of n needs to be to get you a constant. So hope that helped. All right. Andrew, I'll move on to Alicia here. All right. Can you do? I can try the next one. Okay. Let me try chapter 30, number 63. All right. So chapter 30, number 63. I'll even write this down. Chapter 30, number 63. We'll start here at 11:13. Okay, let me switch and even find this question. Okay, so go back to the questions. That's the solutions. Where's the questions for your class? Okay. So number 63. Oh, yeah. Nobody, I haven't worked this one out. No video solutions. Nobody asked it last week. Oh, yeah. Okay. All right, let me just read it here, but it says a wire is formed into the shape of a square with edges of length L. And so let me do my best. Page 1 here. I think it's going to take a while to try to draw a 3-dimensional square. And for my square, I'll go back to my postage notes. So this is, this front edge here is by the camera, and this back here is behind the camera. So this right here is the Z direction. And this is the Y direction. And then outward here is the X direction. And I see that the author's angled it a little bit. He's kind of helped out by drawing lines perpendicular at the midpoint of the square so we can get the center of the square, and says, let's come out here along the x-axis somewhere, so a distance x to a point P, and let's try to find the magnetic field here. All right. Well, I hope kind of the first thing that goes into your mind is we have really 4 straight wires, 4 finite sized wires. And the currents he labels as going this way. So across the top, it comes along the z-axis, then it goes down the y-axis, then it goes back in along the z-axis, and then up along the y-axis. So I'm going to tackle this problem by saying I've got 4 finite wires, and the first thing that pops into my head then is that we have this equation that was derived for Biep's of art, and we can either do the sine form or the cosine form. But this is the magnitude of the magnetic field. So if you take a look then at this top wire and this magnetic field, we need to draw back towards where the current begins, back towards where the current ends, and kind of sloping down perpendicular from the wire, we need to draw to here. And I don't know how well my three-dimensional picture is looking, but for the moment, I am just going to ignore the other three wires. I just want to know what is the magnitude of the magnetic field at the point P. I'm not even going to try to draw the direction. I just want to know what is the magnitude here. Okay, and that's what this equation does for me. So maybe I should just say a 1 here. So magnetic field number 1 would be mu naught I over 4 pi. And I'll pause right here because then this is the R. How far away is it? And so this point P, this is the perpendicular distance away. Oh, maybe I should have put an A because I think it was derived with an A. I put an R, but I think it was derived with an A. So let me put an A back in that equation. This right here would be that A. This would be that distance away. Now, how do I get that? Well, I know that this distance is x, and I know this distance is an L over 2. So if I can kind of point to it so I don't clutter my drawing too much and do Pythagorean's theorem, this is an x squared plus an L over 2 squared square root. That's how far away it is. So this value here for A would be the square root of x squared plus L over 2 quantity squared. That's how far away it is. Okay, now what about the sine of the angle? Now remember the definition of this first angle was, and maybe I should kind of draw our original derivation of this. We had a current, we had this point P, and we said, okay, this perpendicular distance is the A. Okay, so that's what I just did here. That's the A. And theta 1 is this angle that is made by two lines, one drawing from P back to the beginning of the current, and the perpendicular distance. So that would be in this little cubby hole right there. That would be the theta 1. And of course, theta 2 is this angle here. And so it would be this part swinging back. It would be the line drawn to the end of the current. Now, fortunately, we're right in the middle, so we can make our work a little bit easier that realizing that theta 1 and theta 2 are the same, except when it swings backwards, it's a negative. So right here, I could say this would be the sine of a negative theta 1. And of course, sine is an odd function. So the sine of a negative theta is the negative of sine theta. And when you take that negative from the odd function with that negative, you get two negatives, which make a positive. So maybe down here, I'll just write that as 2 times the sine of theta 1. And I'll come down here and make another line. So mu naught I 4 pi. Here's the, whoops, sorry, I didn't mean to write current twice. Here's the square root of the x squared plus the L over 2 squared. And then here's the 2. Now let's talk about the sine of the angle. And so here's that angle. Sine would be the opposite. Okay, so here's the opposite right there. And so I'm kind of looking at this triangle right here. And note that this is the right angle. So the sine of this angle would be opposite over hypotenuse. So this length I need to know. So maybe I'll take a moment to realize that I could get the length of this one by using Pythagorean theorem, where I have this length, which we already wrote, and this length, which is another L over 2. So let me do that. Let me square this. So this would become x squared plus L over 2 squared. And I don't have to write a square root, because when, the length of this squared is that. Then the length of this one squared. So L over 2 squared. Then if you take the square root of all of that, that's how you get the length of that one. Now this can be simplified, I think, to an x squared plus, and let's see, this would be L squared over 4 plus an L squared over 4, which would make an L squared over 2. Okay. So coming back to what I'm after, which is the sine of theta 1, it would be the opposite. So that's this length. So L over 2 divided by this hypotenuse, which we just said would be the square root of x squared plus L squared over 2. Okay. Let me just looking at the answer. I'm not sure how we're going to get to that answer, but I'm far from it, so I shouldn't stress yet. Let's just keep going. All right. So maybe I'll just cancel off the 2's here and see what I have so far. So far I have a mu naught, I have an I have a 4 pi, I have a square root of x squared plus, and I'll just write this as like they do, an L squared over 4. And then I also have downstairs an x squared plus an L squared over 2. All right, so let me say it again. I've only done the magnitude of it. Now let's factor in that these are vectors. So let me get my green pen out here again. Because if I come back to this picture, trying to draw in 3 dimensions, and use my right-hand rule here, this would be making a magnetic field that would wrap around the z-axis. And so right here would be now, before I draw it on here, I'm thinking it might be more helpful to do a cross section. So imagine this current coming right at you. So I'll put a little circle with a dot. And then we are looking for this point P that is actually below it and over here. So I'll put point P like this. It's below by an L over 2 and out a distance of x. So it's down an L over 2 and over a distance x. And so if I take my right hand with my thumb pointing at the camera, I would get a circle that would be making a magnetic field like that. So what's going to make this problem even hard, I thought I'd say it's already hard. What makes it even harder is that this right here is the magnitude of that. So to get its x component, I'll just call this angle here theta, I would have to multiply this by a cosine of theta. And to get the y component, I would have to multiply this by sine of theta. Now, let me not decide which one I'm going to work with first, because let's keep drawing on this. If I draw the currents that is represented by this lower one down here, and so maybe right about here, from a cross-sectional view, it would be going inward. And so if I take my right-hand rule, the second one, and I point the current going in, this would make a magnetic field going downward. And because this point P is right in the center, this distance up here would still be the L/2. And so it would end up making the same angle as this top one. That's a big important key to this, is to realize then that even though this is going to have components, the current down here is going to make it so that the vertical components cancel off. And so I'm not going to have to worry about it. Now the x components are going to add together. So that's why I'm going to do this. I'm going to say, all right, to get the x components, I need to take what I've already derived, which is the magnitude of the field. So I'll just rewrite it here. And here's the big step. I have to multiply it by the cosine of it.
Professor, did we lose an L in the numerator?
Oh, an L?
2 steps up, there's 2 times L/2 in the numerator.
Yes, there is. Thank you. Thank
Okay.
you. Thank you.
I want to make sure I wasn't missing anything. Thank you.
No. Yes, thank you for following. It's funny that the easy things are easy the ones to miss. You know, just a constant number, and you know, when you're so busy focused on the angles and stuff. And yeah. Good. Yeah. So there's got to be an L there. Okay. All right. Now, I'll say it again, because again, this is very visual, that I've got to see how this top current here and this bottom current here made the same strength, and then the angle was the same, so that the y component canceled off. So I'm not even going to ever worry about sine of theta. The y component, I'm just going to say 0. And the x component, I guess I have to take cosine, and since there's 2 of them, I want to double it. But before I even double it, watch this. What would happen with the other 2 pieces? The other 2 currents, the ones that are in the y direction, they, if I were to grab my right hand here, would make a magnetic field, and it's probably best seen. I got something kind of small and pointy. Bummer. I used to have a screw in here that worked really well for something small and pointy, but maybe you can still see it on the camera. I'm trying to say that the magnetic field, right at this point, from this wire going down, would be angled something like that. It would be coming out of the paper like this pencil is. It'd be right at this point, and it would have that same angle. So it would have a z component and an x component. But I'm not going to worry about the z component, because for the same reason, this current over here would make a magnetic field that would point kind of, if I can put it underneath here, pointing down like this. And so the z components of these two would cancel off, just like the y components of these two would cancel off. And so that's a nice way of saying all four of them have the same x component. So I don't need to worry about a y component or a z component. In fact, I could just write, and probably should to have completeness of the problem, the y component is going to come out to be 0. The z component is going to come out to be 0. And the x component is just the x component of one of them multiplied by 4, because there are 4 of them.
Should the you have the like square root of x squared, and it says L squared over 2. Shouldn't it be L over 2 squared?
No.
Or it's another step above. Oh no? Okay.
Yeah, that was back here because that was the length of this one. If it was just L over 2 squared, that would be the length of this one.
Oh, I see. Right, because sine is opposite over hypotenuse, right?
Yeah, right. So
Yeah.
you got right. And to look carefully at this triangle, that's the hypotenuse. Right.
Got you.
Right. Okay, so I think we're getting close now, finally, because that visual picture, I think, was the tough part of this problem. And realizing that I don't have to worry about the y component, I don't have to worry about the z component, and then I just have to do the x components one time and then multiply by 4. All right, maybe I'll bring it back into the camera's view so I can write the next step. Mu naught the I, and thank you for the L. Now the 4 cancels off, and so I'm just left with a pi downstairs. And one of the square root is x squared L squared over 4. And the other square root is the x squared plus the L squared over 2. Now, to finish this problem, let's take a close look at this cosine of theta. And to do that, we need to come back to our picture. Of course, I drew the picture here as a cross section, as this is theta. Let me continue with that cross section. If I were to draw a line from this top current to this point, this right here would be 90 degrees. And so what I called theta, and then of course that's 90 degrees, and then this one here, all 3 of those has got to be 180. So you might say this one in here is 90 minus theta.
I think it might have frozen again, Professor.
I think I'm going to restart everything. Well, I'll restart the camera here. I think we'll get through it one more time here. But I think I need to just, on the break here, reboot everything, my phone, my laptop, maybe even my Wi-Fi. But it's freezing on my laptop, so I think there's something between my laptop and my phone that is playing games with us. And that kind of would make sense. I don't think I have restarted in a while. I just keep closing down and it goes to sleep. So I'll do a reboot. Okay, so what I was trying to point out when I think it froze was this little triangles in here, that if this is theta, then this one is 90 minus theta, which makes this one up here a theta. So knowing that that one is the theta, and coming back to page 2, where I'm trying to write the cosine of theta, I can look at this and say cosine of theta would be adjacents. Okay. And so in this 3-dimensional picture, this right here is my theta. And so the adjacent is the L over 2. So this is going to be an L over 2 divided by the hypotenuse. And the hypotenuse would be this piece going back. So not the hypotenuse of this one like we did earlier. It's the hypotenuse of this one, which we also did earlier back when we were doing the sine of that. And that's the one that is the square root of the x squared plus the L squared over 4, the L over 2 squared, which is the L squared over 4 here. And so hopefully this will be our last step. Let's see. I got a mu naught, and I got an I, and an L and an L there make L squared. That 2 can go with the 2 pi. These two square roots are the same, so that would just be an x squared L over 2, 4 without a square root. And then this square root has nothing to group with. So I'll just leave it as a square root. And do we match? Yes, we do. Yay! And so that's what they got out of that. Wow. Good problem. I forget who asked that one, but yeah, good problem here. Let's see, that was number 63. Alicia. All right. Hope that helped, Alicia.
Yeah, thank you. Because they did it a different way where they broke it up into 8 pieces, and I couldn't understand why they did it 8 pieces instead of 4, but I guess the solutions are just, yeah.
Okay, well, I won't waste you guys' time in looking at it now, but
yeah,
I'd be kind of curious why they did 8. Huh. All right, now, I see, Daniel, you've got one. Would problem 63, the one you just did, be something, too long for a test, so it's not a, yeah.
Yeah, I was just wondering if this would be like something we could expect on a test, or if this is too long for a test.
Yeah, this would be too long. I was just trying to think of what might be a modification that would be kind of test appropriate, so I could say. So let's say it wasn't. Oh, you know what would be a good one like that would be appropriate? Would maybe, let's say it's not a square, but it's 2. The top wire and the bottom wire are infinitely long, because then you don't have to worry about this first step where you've got to figure out that angle, and then you're only worrying about this being twice. So, but I should just answer your question. Your question is, would it be too long? Yeah, that it's too long, and it actually turns into a little bit more test of mathematics than physics, but maybe not, because most of it's visual, and I don't know how to put the visual as, do I categorize that as physics or math? But the visual is to get the angles involved in 3 dimensions, but then the physics is the math then is to represent the trig functions with those visual pictures. So I would say there's really 2 reasons why I don't think it would make a good test question, because number 1, it's a long problem, and then number 2, there's a lot of mathematics of the sign of the angles, which you do get from the visual, which I suppose I should put as physics, but it's not. It's the physics of visualizing 3 dimensions. It's not the physics of magnetic field. So you can see I'm not wrong. I wouldn't put this on a test. That's the short answer.
Can I see the second page again? I just want to take a screenshot, so I don't have to.
Yeah, sure.
Yeah. Okay, thank you.
Mm-hmm. Actually, that's a great idea. You guys probably do that with screenshots. I learned something interesting that maybe it's obvious to you. It's never happened to me before. And it's not like I'm always the host of the Zoom. Now, with you guys, I'm always the host with the Zoom. I get that. But, I have a number of meetings with faculty and departments. And maybe because we don't record them, that's the only thing I can figure. But I had a student that is finished up in Cal Poly, and he's majoring in electrical engineering, and he's doing a senior project on solar panels. And so he finished our program about 2 years ago, and he contacted me because he remembers me telling him and others that I have a 5K solar panel on my roof, and I love it. And in his senior project, he's got to interview, and I was shocked, 50 people. And they don't all have to be owners of solar panels. Like, he's got to interview people who install them, people who build them, people who design them. But in my case, he knew I had them. So anyway, I Zoomed with him yesterday, and he wanted to start asking a bunch of questions. And he goes, and for my project, so I can go back and re-listen to your answers, can I record it? And I said, yeah, of course. So he hit the record button, and I got this dialog box that says I have to agree to join in when it's recording. Do you guys get that?
No, I don't.
We get it says that this meeting is being recorded, but I'm guessing, so you weren't the host of that meeting?
No, so I wasn't the host. He was the host, and it just said, and as soon as he hit record button, a little box said that, okay, for me to continue, I have to click OK. I guess I'm acknowledging that it's being recorded.
Actually, now that I think about it, I did get that once. It was a webinar with a few different universities. And they started recording the meeting. And yeah, I guess it's just so you're aware, for legal purposes or whatever, that you're being recorded.
Yeah, I get why you might put it in there, but I just had never seen it before. And I go, hey, I wonder, and it just made me think, I wonder if my students, every time I start record, if they get that little box, and of course they just click on it, they don't say anything, but I don't know, maybe because it's a group meeting.
No, we just get this meeting is being recorded. Yeah, it could be because it's just 2 people. That actually might be if it's just,
No, I think it's pretty rare. I think it's just for, like, certain meetings, they might have it set up that way. Like I said, it was just for a webinar. Like Princeton and a whole bunch of different universities were giving a transfer process, and there was probably 100 to 300 students sitting in there. So I don't think it depends on the size of the meeting. It's just how the host has it set up, I guess.
Yeah. Or maybe it's a fact that you send the invite through a SBCC email to other SBCC emails, so it just might pick up that we're students and not ask us.
Yeah. Okay. Yeah. I'm really glad I asked. I was just going to blow it off and said, yeah, they get one. But no, it's just, okay. It's just, sometimes you do, sometimes you don't. Maybe this is part of the learning, Zoom's all new to me. Never Zoomed
It's probably
before.
something in the organization Zoom settings is what I'm guessing. Because there's a whole, like, the legality of, California is a 2-party consent, like, recording state, but also this, because it's like a public Zoom meeting, the right to privacy, I think, wouldn't necessarily apply in this setting because it's like there's other students here. So I don't know.
Yeah. So, like I said, just picked one of these questions that, kind of curious, but wouldn't invest hours of time to figure it out. So, hey, okay, so let's take our break. I don't see any more questions here in the chat, although I'm sure you guys have lots of more questions here for me, and I'll come back at let's see, our second one's at 12:30 here, so we'll see you guys at 12:30. How's that?
Okay, see you in a bit.
Sounds good.
Thank you.
Thank you,
guys.
Professor.
Yeah.
Oh, thank you.
Thank you.
Yeah, you're welcome.